Okay? So we've got to say the rate of change of pendulum velocity. So we're going to have an equation for the rate of change of pendulum velocity. Unfortunately, that rate of change is going to depend on the pendulum position. And position and velocity have a relationship. Okay? So that complicates the model. This is a significantly more complicated model than the one for the depth of the water in the container. So, rate of change of pendulum velocity with respect to clock time is what? I'm saying it's dv dt equals negative 10x. X is going to be the position of the pendulum. The position of the pendulum relative to the straight down equilibrium position. I'll write that down in a minute, okay? But let's get the units of dv dt. Okay? Now this means instantaneous rate of change of velocity with respect to time. But we're going to use it as an average velocity, and it's just going to be a change in velocity divided by a change in time when we actually apply it. Okay? Fourth semester well, actually in first semester calculus you get a little bit of this, because you can actually solve some of these equations, but not this one. Yeah, but you get this notation. Okay, that's not too relevant to what I'm saying here though. dv dt then would have units of change of velocity divided by change in time, right? Change in clock time? Well, the change in velocity has units of velocity, right? If I subtract two velocities, I'm going to get a like term, okay? And every one of those terms has the units of velocity on it, okay? So I'm going to use centimeters per second for units of velocity, okay? So that's the unit of our change in velocity. What's the unit of time? That's a second, right? Okay? And I'm going to just write it as this. I'm not going to do the algebraic simplification. Although y'all seem to have really good algebra skills, there might be a little confusion. Some of you might get a little confused if I do at this point. We don't need to do that. We're just going to write it this way, okay? And then we say when x is in centimeters, relative to the equilibrium position. Everybody know what I mean by the equilibrium position? Yeah, when the pendulum was hanging here and not moving, that's the equilibrium position. When it was oscillating back and forth, the equilibrium position was halfway between here and here, sort of. Yeah, actually the swings are getting slightly shorter each time, so it's exactly halfway between the here and here, but in the ideal case that would be so. Okay, now that means x is positive on one side of equilibrium and negative on the other, right? So the signs become extraordinarily important in this model, okay? So now we're just going to assume that at t equals 0, x equals 12 centimeters. I don't want to use 10 again. I use a nice round number, but I'm going to use 12. Still easy to do this. X is 12 centimeters. And the velocity we're going to say is 8 centimeters per second. Okay? So, I'm just going to say, okay, go ahead and work out what you can. For the next let's say 0.02 second interval. What conclusions can you draw for what's going to happen to this pendulum in the next 0.02 seconds?